Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBC CPS IAC. It's my pleasure to introduce today's speaker, Dr. Dheeraj Nagaraj. He'll be speaking on fine-tuning diffusion models via intermediate distribution shaping. Dheeraj Nagaraj is a research scientist at Google DeepMind. He works on various problems in theoretical machine learning, applied probability, and statistics. His current work focuses on sampling generative modeling with diffusion models. He completed his PhD at Lab for Information and Decision Science Systems at MIT in 2021 and his dual degree in electrical engineering from IIT Madras in 2016. Over to you.
Thank you. Thanks a lot for coming. So I'll be talking about my recent work on which was published in ICLR 2026. This is about fine-tuning diffusion models via intermediate distribution shaping. I'll go through all of these terms. I'll kind of introduce diffusion models and more interesting aspects of diffusion models and why we should consider them and what are the challenges in fine-tuning them and post-training them like we do with large language models which are autoregressive. So let's go into this. So this is these are my collaborators. I think now Gautam is now in UC Berkeley as a PhD student and everyone else is right there. And Shan was my intern when this happened. Most of the work was done by these three and I was more on the advisory role. So, okay, let's look at generative modeling and think about RL alignment from a conceptual point of view. So what does pre-training of a generative model do? We are given a large data set x1 to xn which is distributed as p. It's an idealization. For example, it need not be independent. I mean, it's usually not, but let's assume that x1 to xn are independently drawn from some p. Our task is to obtain more samples approximately from p. Okay, so that is the pre-training. Okay, so what are the examples? You can go and crawl the internet for LLMs. That was increasingly what people did, what people used to do, but at least since 2019. Maybe now things have shifted more to getting better curated data. And there is something called Lion5B, which is images with captions, right? Which is crawled from the internet. So you get 5 billion images of what people have posted publicly. You take that and the captions, and you try to train image models. Okay. So the problem with these things is that it might not be pleasing to the human eye. It might contain wrong answers, and it might not be what you want. Okay, so that's the problem with pre-training that we hope to solve with RL alignment. Okay, so let's go into the mechanics of how these autoregressive models behave, which is the current generation of neural networks. Okay. So these generate joint distributions coordinate by coordinate or token by token, and in an autoregressive way. So how does it do? There's a neural network. Initially, we don't give it any input. It produces something from the joint distribution G, let's say for this case, and then it looks at its own output, which is G, and then it predicts the distribution of the next token and samples from it. And now that is E, and then N, E, R, A, T, E. At every point of time, it looks at what it has generated till then, and then tries to predict the next token, and so on, and then we end up with an entire sentence or paragraphs and essays which look legible to us. Right. Okay, so now let's say we are given a Sudoku. This is not something we are writing. We do linearly, word by word, sentence after sentence, and so on. It looks autoregressive. Suppose we want to solve this Sudoku, right? How do we solve this? Maybe we can, autoregressive models would go in and start filling these numbers like this, right? So, I mean, is this the natural way in which humans solve it? I have never solved a Sudoku like this. I always look for easier spots to fill it in and then go in a non-linear way. And then, is this the best way to solve it? I highly doubt that's the best way to solve this. And maybe if we are faced with a problem where there is no structure where generating one by one makes sense, we want to move beyond autoregressive models. And that's where diffusion models come in, right? So diffusion models work with a different perspective. So this is the other kind of the popular kind of generative model which is used in practice. So what the principle here is simple, okay? So there's a destructive process called the forward process, right? And that, it's you take a nice image like this garbage truck here and you destroy it by making it white noise. Okay, so what did I do here? So I evolved it with respect to a stochastic differential equation. So this writes as dxt is equal to minus xt dt, that is go towards 0. It's an ODE which goes towards 0 exponentially fast, but then I add this diffusion, which actually does not let it go to 0, it keeps on adding noise. Eventually this becomes purely white noise, right? And you get this image, and it's easy to do, fairly easy to do, 2 lines of code, you can destroy an image very easily. The thing is the reverse direction, which is the reverse process or the constructive process, is what we want to learn with a neural network, and where we want to start with this pure noise and when we want to sample an image from it, from the same distribution. So this has a form, very specific form. This is another stochastic differential equation. So here we can see that if this was going towards the origin, this is going away from the origin in the radial direction. And this had a diffusion term, this also has a diffusion term. But what is this extra thingy? This is this 2 grad log pt of pt minus t of xt dt. So this term is what gives you the signal from this about the data distribution. This is a statistic of the data distribution. What is this pt? This is the density of xt in the forward process. Okay, so there's a density function, and you estimate grad log p of xt, and you can use that to simulate a reverse diffusion process, which will give you an image when you start from noise. Okay, so this is how diffusion models work, and so basically we learn the score function. This is called the score function with a neural network using something called the Tweedy's formula over this gigantic data set, and when we run this algorithm, which is any discretization of this Ito process, and then we get an image, and that's what diffusion models do. And this is the score function. Okay, so to give you a nice visualization, a score function is like a compass which tells you where to go from a noisy image to a clean image, right? So this is a noisy image. Okay, you can think of an image as a vector in very high dimensions, and so in that vector in that high dimensions, there's a clean image and a noisy image. It will tell you roughly what direction you want to go in, so that you go closer to the clean image, right? So that's what it does. Okay, so right, so we had so we originally started with LLMs, which was in discrete space, and I showed you Sudoku, where I told you we don't want to solve it in sequence. Okay, and then went to continuous diffusion models. Now let me connect some of these threads and go to discrete diffusion models. Okay, so here we spoke about continuous noising process, we got continuous diffusion models, right? And then we have discrete noising process, we get discrete diffusion models, right? So it's simple. So basically you use a discrete Markov chain to destroy information, and then you try to reconstruct it by using statistical estimation, right? You reconstruct it in distribution, not in sequence wise. Okay, the first work here is probably Austin et al., and there's a lot of variants and follow-up work. Okay, so the first example of this is called mask diffusion, right? So what is the point of mask diffusion? You suppose you start with a clean word like generate, right? And then you go in and flip each to mask with probability p. So it's an absorbing state, right? And then rest of them are left here. So if you look at this, you can see that, okay, it may be generated, but it's slightly masked. It may be something else too. So there's a real statistical estimation to be done. Given these are known, what is the probability distribution of this, right? Okay, so you flip more, now it's very less clear that it came from generate. And then finally you end up with all mask, where you have completely destroyed all the information you started out with. There's no mutual information with respect to what you started out with. Okay, so now how do these models actually work? So you suppose you started out with demolish and you noised it, and we got all these things. And then in denoising, what you do is start with again this full noise, and then you apply predict original and apply Bayes rule, right? You use a neural network to do statistical estimation as to, okay, if this is my sequence, what is the distribution of these three things? And you go and flip those two to that distribution. Okay, so and you keep on doing this a lot of times, and then you end up with a different word. So now you started out with demolish, ended up with generate, because you already destroyed this information. So what is it that I'm reconstructing? I'm learning the distribution of words, and I'm drawing another random word, right? Which is like, these are both from, let's say, the dictionary. Right. So That's how it works. You can see in what order we generated the letters here. And if you had an autoregressive model, it would generate one by one, G, E, N, E, R, A, T, E. Okay. So that's the difference between these kind of approaches. What do you mean? No, so there is randomness in the sampling, right? So you have a neural network which will predict the posterior. So for example, okay, so probability of this being an E is, let's say, 0.005 or whatever, 0.05. So it will go and toss a coin and say, okay, this is an E because it was from that sample, it says it's an E. It could have been A also, it could have been S also, depending on the probability of these things. But given that we have generated NTE here, but these become posterior probabilities. Right, so they are all dependent generations now. So that's how it works. Okay, so there's other ways of noising these things. Other is the multinomial noise. Okay, so here let's say we have demolish. We go and pick these two positions. I'm denoting this by blue, but it is actually not seen. So I'll go and replace these with something independently sampled, right? K and H. Now it kind of looks like demolish, but it's not 100% sure. We can't be 100% sure it came from demolish. Okay, now I go and destroy more and more information until I end up with this. The blue is not actually visible. I'm just giving it to you so to show you how I came here. Okay, so you have this UPGEAIHE, which makes no sense. It's not a word, and it's way out of distribution of English, right? And we have successfully destroyed information. This is completely independent of where I started out with. Okay, so now how do you do denoising? You start with this full noise, okay, and then you go in and say, okay, so suppose at step 4 I have this, okay, what is the posterior probability of these letters? Okay, this is predicted by a neural network. We learn these things with a large corpus, and then okay, it flips those, and then it will again do that. Okay, given that at step 3 these are the things, what are the posterior probabilities of other positions, and so on, and it will generate all these things. So the advantage here is that multiple flips at the same token are possible. This allows backtracking. That is, if you, for example, H went to L and L went to T. So you did multiple variants of this. Okay, we can, for instance, we can see this as having rough drafts, and we can refine it by correcting the mistakes. Okay, so okay, let's look at the 3 kinds of models I kind of introduced here. One is the autoregressive model, where the generation order is causal. In mass diffusion and multinomial diffusion, it's arbitrary. So you can generate in different kinds of orders depending on your sampling algorithm. There are many algorithms which also play with the structure of what is the order to denoise, but in the simplest method, you pick it at random and then kind of denoise it. Okay, noise versus signal. In autoregressive, whatever you've generated till now is correct, and then you generate based on that in the future. In mask diffusion model 2, whatever is mask needs to be generated, whatever else has already been generated, it's part of the final output. In multinomial diffusion, it's unknown. We have no idea whether it is random noise or should be flipped or it should be kept, right? So that is unknown. So tokens per call. So if you ask one forward pass on a neural network, right? So how many tokens can you generate? You can generate 1 here, but you can generate 1 or many in diffusion models, which is their primary advantage. Backtracking in the sense that, okay, in autoregressive models and mass diffusion models, it's not fundamentally possible, but you can write algorithmic, changes, hacks, which can get you there. Yeah, so go ahead. Neural network. Yeah, I mean, that depends on your sampling algorithm, right? So you don't have to, it depends, so you don't have to enforce that it corrects it. So eventually, even in the simplest ones towards the end, it will actually not sample the same thing again and again because it already makes sense. Changing it actually goes out of distribution. No, it determines that itself. Threshold is the sampling algorithm territory. Again, it depends on what you want to design. No, in the sense that it's a vacuous thing, you end up with the same sentence. So, yeah. So backtracking is allowed in multinomial, but it's not allowed in the others one. I mean, in painting. Okay. So what do you mean by in painting? So you have paragraph 1 and 2, and you want to ask it to so 1 and 3, and you want to generate something in the middle, right? And it's actually easily possible with the mass diffusion models. right? But it's not easily done with autoregressive. Again, you have very large LLMs, you can say, okay, this is my paragraph 1, paragraph 2, write something, joining them, it can do that. It just happens with scale, you can modify all this, but I'm just talking about very standard implementations. Just like that, it's cleaner here. Okay, so these are some of the comparisons. Like I said, algorithmic changes can allow more features for all these models. Okay, so how do we learn the discrete diffusion models? Most proposals hinge on predicting the original unnoised sequence given a noisy sequence. So suppose original sequence was deep, and then I'll go in and make it like this. I mask out these two. Okay, and then what does my neural network do during training? I input this mask sequence to it, and then I give it, say, okay, we are at step 2, that is the signal to noise ratio, kind of. It's a proxy for the signal to noise ratio. And then we wanted to predict deep. Okay, by predict, I mean, of course, you can't perfectly predict it. What I'm saying is you predict the posterior probabilities of the masked positions, right? So for example, it could be deep, it could be beep, it could be any, or it could be jeep. Okay, so it tries to learn the distribution of those things based on this. But in the data points we will have deep and then this thing, right? And you want to find an algorithm which models the posterior distribution. Okay? It's fairly simple using cross entropy laws. Okay. This is the mass diffusion. This is the multinomial diffusion. Let's say you have deep, it could be corrupted to ZEEO. Okay, it could have come from ZERO being corrected to ZEEO. Why is it coming from deep? Right? There are various possibilities, and it tries to learn all of these things. Okay, so okay, what is the exact loss function you use? There are many proposals. The simplest thing is cross entropy. There is ratio matching. There's SED, and then there is various proposals that we have also given out. And but all of them morally do the same thing. They do posterior approximation with various losses. So that is a good question. So basically, if you want a production grade thing, okay, so there is a context and then there is a generation. So what people do is something called block diffusion then. Okay, so you have, let's say, a context like this. Okay, so and then you generate in blocks of 256, let's say, for example. Okay, and then you append this to context, and then you generate the next block of 256 with a diffusion model. So it looks at these two as context, but then these are generated in parallel. So this is how production level systems deal with this. Yeah. So right now, okay, so originally when they started out, it was hope that, okay, so let's say that there are many things to be addressed here. The quality question, I have not seen it do better in language. Let me be honest about it. It has done well in discrete and discrete continuous diffusions have done well, let's say in molecule modeling, sequence modeling, and so on, where there is no autoregressive structure where everything depends on everything. But language in itself is written one by one, and we have designed language that way, we have designed speech that way, right? So that it actually, autoregression actually helps it, right? And diffusion models, as far as I know, have not shown any benefit over autoregressive models. Where it matters is very nuanced, it is in speed, okay? Because you're generating multiple things at a time. Specifically, there are two things here. One is latency, other is throughput. Okay, so I'll give you an autoregressive model, and I ask you, okay, you can take all the resources you want. Can you generate it for me as fast as you can? The answer is no. You cannot go to arbitrary speeds because frequency of the clock of your thing actually constrains it, because you have to go in sequence. Even if I give you infinitely parallel compute, you cannot actually do autoregressive modeling very fast. Okay, so suppose I am very resource rich and I just want it at 1000 tokens per second. So you go for a diffusion model, it can actually deliver. But what is the cost? It actually consumes more number of floating point operations for the same generating one token, right? So if you are resource rich and you are not able to consume your entire hardware, right, and you want fast inference, you go for a diffusion model. You want to run it over many iterations, it's faster. So latency is lower, but throughput is also lower, because you can't parallelize multiple things at the same time. So that's the nuanced take on this. So a lot of companies are coming out and marketing this for that. Okay, so you are a person and you don't trust your data to go into the cloud. You have your own GPU here and you want to run it as fast as you want. So if you host an autoregressive model, it will probably give you 200 tokens per second. But if you host this, it will give you lightning 5x faster. So of course you would go for this if it gives you the same quality. Of course, at more power consumption, but that's a different matter. Yeah. Okay. So now let's come to the other arc of this, which is the fundamental thing. This was a large detour as to how diffusion models work and why we care about them and so on. Now let's look at post-training of generative models. Okay. So in the first slide, we thought about pre-training. We just wanted to mimic the data we had, large-scale data. We collected it from all kinds of sources. Okay. So now what is post-training? So for example, it could include instruction tuning. Okay. So we want it to be in a question answer format. So if you make it memorize or make it train on entire books, it will not be in a question answer format, right? It will be like a textbook or whatever. So, but usually chatbot applications, you have a question and then it has to answer. It has to recognize that format and it has to stick to that format, and you do something called instruction tuning. Okay. So you might want it to refuse to answer harmful questions, right? So that is also part of this post training. And you might want it to stop hallucinating. You want it to increase factuality of the answers, right? And you might want to make the generated images pleasing to the eye, right? You might see some random images of the internet, and it's generating random images from the internet. You don't want to see it. You want to see good images. And how do you make them pleasing to the eye? So maybe you take some very nice photographers' images, but these are more expensive. So you collect 10,000 images from nice photographer, and then you train on those. But these are limited. It's not in billions, it's in maybe thousands. Okay, so we want to improve the aesthetic quality and readability of the generated text. We don't want it to read like a chat section and some comment section of some random blog. You want it to read like something a professional writer has written. Right? So that is aesthetic quality and readability. Again, if you go and ask a professional writer to give you something for a custom, it will cost a lot because they charge a lot. So you get a lot less data of this form, but it's more useful. It has higher quality. So this goes in post-training. Okay. So what is RL post-training, RL alignment? So this is more specific. In this case, we are given a question X and an answer Y, and we have a reward model. Let's say R of Y given X, and for each task. Okay. So the reward is high if we are doing it well, and answer is the right answer to the question. If it is low, if it is the wrong answer, or it's not completely correct. Okay. The task of RL alignment is to tune the pre-trained model to generate answers with high reward value. That's all it takes. Okay. So, so this is the thing. Okay. So now let's look at, these are generative models. So these do posterior inference. So basically, given a question X, what is the sampled answer Y given X? Okay. So it actually models a probability distribution. Okay. So P naught of Y given X, okay, is the likelihood of the answer Y given X with respect to the reference model, which is the pre-trained model, right? And now we want to, we have something called the policy model, which is P theta of Y given X, which is what we are trying to train. Okay, this is the likelihood of answer Y given question X. Okay, we formulate this in terms of something called the entropy regularized reward maximization. Okay, so what do we want to do? We want to do arc sup over theta of R of Y given X minus KL divergence between these two posterior distributions. I hope everyone knows KL divergence. It's the ECE department, so it's more common here. So yeah, so we have R of Y given X. Okay, the first part is clear. Why do we want to maximize reward? Because we want higher reward. Okay, but why are we adding this regularizer? It's because we don't want to drift too far away from the pre-trained model, because it has a lot of unstructured knowledge, as we say, and you don't want to lose it. Okay. So we get something like reward hacking and mode collapse, which happens if we ignore this term. Okay, so this is roughly what we're doing. Okay, so let me show you a picture. Okay, so we had a, let's say this is the reward statistics. Okay, let's say the reward distribution. If I asked a question, so it answers many questions. You take a Monte Carlo sampling of the answers and then plot the reward distribution. Let's say the pre-trained model gave a reward distribution like this. So it is capable of answering well sometimes, but not all the time. It gives you garbage answers sometimes too. Okay, and this is without regularization. Your policy would answer something like this. It is overfit at the extreme. Why I'm calling it overfit is because the reward models need not be useful at that point of time, in the sense that you've gone and trained another machine to tell you if it is the right answer or not, and it goes so out of distribution that it hacks the reward and starts spouting nonsense at this point of time, right? So you don't actually want that. So what you want is this entropy regularized thing, which gives you high reward things compared to the pre-trained, but is also not too far away from the pre-trained model. right? So this is what we want as the reward distribution. Okay. Okay. So now, okay, let's look at how we do this in the autoregressive models. It is actually fairly straightforward, and it was also, this formulation made sense because these quantities are available for LLMs, autoregressive large language models. Okay, so you have a neural network input and output, you generate one by one. So basically what this means is that the model actually has access to this kind of a decomposition of this probability distribution. So answer y is actually a sequence of tokens y1 to yn given x. Okay, so what it models is, it models y1 given x and y2 given y1 comma x and so on, yn given all things y1 to n minus 1 given x, right? These are all known to the model. If you pass this sequence, it just gives you those probabilities. Okay, and now you can you use this and compute the KL divergence very easily. It's actually very simple. You just take the log of this under the distribution of the second one and you're done. And then you can use your favorite policy based RL algorithm, for example, reinforce works, PPO works, actor critic works, GRPO, anything. It just works as long as the reward is not too crazy or something. Okay. Okay, so it's done and everybody uses this, and now we are proving all these open math problems with LLMs using partly these kind of post-training methods. Right. Right. So now let's go to the case of diffusion models. Okay. Yeah. Sorry. They're not differentiable. In general, they're not. Yeah. So yes, it's very tempting to do that, but okay, even when it is possible, it tends to terribly hack the reward. Okay, so now we have this garbage truck. Okay, so this is my prompt. So what do we want for a text to image model to do? I'll give a text like this. Okay, I want an image of a garbage truck. It will start from noise, that is y5, and then it will go to y4, y3, y2, y1, and y0, which is a garbage truck. We are slowly denoising this one by one. Okay. Now, in diffusion models, what do we have access to? We actually have access to conditional likelihoods. We don't have access to marginal likelihoods. Right. So what do we mean? We are given partially denoised state yn. We want to denoise it more. What is the posterior distribution of yn minus 1 given yn and x? Right. If I give you an image y and tell you, oh, this is high quality, what is the likelihood of this image under a model? I cannot tell you the answer to this. Right. So if you can't know the marginal likelihood of an image or of an output given the question, so then you can't use the scale regularization. Right, because you have no idea how to compute it. Okay, so of course the community got to work and thought, okay, how do we actually do this? So the first thing they came up with was something called trajectory KL instead of marginal KL. It's called DPOK. So again, this whole trajectory y5, y4, y0, etc. It's a joint distribution of various things in a higher dimensional vector space. So, okay, you take the joint distribution of this entire trajectory and you regularize that with respect to the thing. Okay, so this is called DPOK and it works well in some situations. The problem with this is that it leads to subpar results, okay, as shown in future work, and because it's too conservative. You cannot constrain the entire trajectory, right, and tell you how to go to the entire way and then expect it to still work. And it has something called initial value function bias problem. It's because we are using neural networks, you don't have independence of the initial point and the final point. It's a more nuanced question. I can chat offline about this later, but it's a real problem which can creep in. Okay. So DPOK is not usually used. And the other thing is that, okay, people thought, what if we just remove the KL regularization? Okay, so this is a catastrophic thing. So this is called DDPO. Okay, so basically you treat the denoising process as a Markov decision process. Right, you have, it's a control thing. You have two controls, that is the drift. Basically, that's all you model. So yn minus 1 till whatever, you get a reward and you change this function. So it's classical RL. Okay. Okay, action is the denoising kernel, and you maximize the reward with your favorite RL algorithm. Right. Okay, so the problem here is that it can cause mode collapse or become unstable in large scale training. Right. So you cannot actually have, let's say, come up with 1,000 new images or 1,000 new prompts and say, okay, I have a reward function for this and I want it to become better, and it just doesn't work at that scale. Right? Okay, so our work from earlier this year or late last year meant to solve this, meant to investigate methods here based on, of course, well-established lines of research as to how we can actually give the best algorithm to post-train diffusion models. So an alternative is a backdoor via a rejection sampling. Okay, so what do? You have this samples. Let's say this is the space, and these are the samples generated in some high-dimensional space. Okay, the red ones are the bad samples, and the green ones are the good samples. And my reward model says, okay, let's say it gives it greater than or equal to 0.5 here, less than or equal to 0.5 here, and we want to only generate something greater than or equal to 0.5, and we will accept this and reject this. And this green thing is the target distribution. So what do we do here? So basically we create a large data set of accepted samples and fine tune on these accepted samples using the pre-training algorithm. Okay, so this is called rejection sampling fine tuning. Okay, so now, okay, let's actually, I just hand waved how do we do rejection sampling, but let me actually show that what RL algorithms are trying to do with the entropy regularized reward maximization is the same thing as rejection sampling fine tuning, at least with perfect training. Okay, so now we had this entropy regularized reward maximization problem, and let's say theta star is the solution to this, and p theta star is basically a tilted version of this. So p theta star of y given x is exponential of reward divided by beta times p naught. So basically it upweights the samples with high reward and downweights the samples with lower reward by exponentially. And okay, so is there a way to generically produce samples from p theta star? It is actually possible. Statisticians have studied this for decades and decades, and it's called rejection sampling. So we want y given x comma accept, okay, should be like p theta star of given x. So that's called rejection sampling. Okay. So now the classical rejection sampling says that probability of accept given y should scale as exponential of r y given x minus r max divided by beta. Okay. So basically, if you okay, I generate something from the pre-trained model, I accept it with this probability, and then I I collect a new data set with these accepted samples, and that is a sample from my post-trained model p theta star theoretically. But then you'll have to do a lot of acceptance rejection, that is low acceptance rate will hinder efficiency, right? Okay, so an efficient proposal here is to generate y1 to yn, which is from the pre-trained model, and then we calculate the reward for each of those, and we keep top k out of n. So here we don't actually, maybe we're not forced to throw out 99% of the thing, we keep top 40% or 25% of the thing all the time. Okay, so this is what is done in practice. Okay. Okay, this is not something new. This is all very, very well known in the literature by, let's say, RAFT by Dong et al. And then there is rejection sampling based ideas are also used in LLM fine tuning. And then, of course, best of n alignment this is called. So basically, you generate n trajectories and then keep the best one and fine tune on that, right? And there's more things which been learned like bon and so on. So it's a well known idea. So to give you a pictorial description of this, you have an input x, you have a pre-trained model, you generate multiple independent samples from this here, y1, y2, y3, y4, and then you accept the high reward outputs. Okay, let's say y1 and y3 are the high reward outputs, and then you retrain with the accepted samples with the pre-training algorithm, right? So this is called GRAFT, okay? So mathematically, this solves scale regularized reward maximization with a reshaped reward. To give you an example, okay, so let's say we have a preference reward. Okay, so you generate y1 and y2, and you get rewards r1 and r2. You keep y1 if reward of y1 is higher. You keep y2 otherwise, right? So now I'll do this rejection sampling fine tuning. What is my final distribution? It actually is like, it turns out that it solves entropic regularized reward maximization with the reshaped reward. And the reshaped reward is actually the CDF function of my reward. Okay, it is actually easy to see. So you had a reward function, you wanted to do RL with that reward function. But I'm saying there's this efficient algorithm with the which does reward shaping. by a rejection sampling, where you just replace the reward with its cumulative distribution, which is again another monotonically increasing function. So it shouldn't change your goals too much. Okay. So in this example, okay, let's say the actual reward was 0.85, right? But then in the distribution of the rewards, it's the 99th percentile reward, and the reshaped reward here will be 0.99. Okay, and then reward was 0.1, and it was a 30th percentile reward among all the generations. The final reward would actually be 0.30. So that's the kind of a reshaping we are talking about. Okay, so of course any kind of rejection sampling, we can kind of obtain this kind of reshaping, and this is just one example of it. Okay, so now let's go back to the question of diffusion model. So this applies to any kind of generative modeling. I did not tell you how I generated it. It's just that I was able to generate it. That's a pre-training algorithm. I rejection sampled, and then I used the pre-training algorithm self-generated data, and it gave me better samples now. Okay, so so can we do better using the structure of diffusion models? Okay, so that's the question. So because there is a specific structure here, you start with noise, an image white noise. So can I use this structure fundamentally? So here the prompt is garbage truck, and the reward here is text to image alignment. So finally I have, let's say, an autorator, which will, like a clip model or whatever, something which will look at this image and look at this prompt and tell me, okay, is the image, does it conform to the text written, right? So it's a very simple ML task, and I'll get the reward. Okay, so now my thing is, you don't have to go till the end to figure this out. Actually, if you look at this part, it's already clear that it's a garbage truck and it will reach a high reward, right? Do you actually have to learn the last step, even this, right? Because any diffusion model, if you give it this pre-trained diffusion model, if you give it this much and just do the last step, you will get a fairly good enough image. So you don't need to actually train the last step. Okay, so the last step would be a nuisance in the training. Okay, so the idea here is to train early transitions with high reward, which have high reward variance. Okay, and then not train the last part. Yeah. Okay, so we have input X, and let me give you a schematic here. So we generate multiple images. Okay, out of this, let's call it y1, y2, y3, y4 through this denoising process, and we accept high reward samples. Let's say y1 and y3 are the high reward samples. And we only train steps n to k. We do not train the steps k minus 1 to 0, right? Because this is where most of the reward increase happens, right? And training these requires more samples, and we don't want to waste training, and we don't want to train something which won't affect our reward. Okay, that is the high level idea here. Okay, so okay, let me show you a picture. Okay, so in the last image here, the reward variance is 0 given the final generation y, because we know the reward, right? It's a, let's say it's a deterministic function for now. Okay, so let's say we observe this picture, right? There is some reward variance. Okay, it can still go to something which does not conform to the garbage truck, right? It's small probability, but it's still a probability. So reward has some variance, but if I show you here, reward has a lot of variance. We have no idea where it will go, right? So that is one trade-off. So of course we want 0 variance in the reward to learn the best. But what is it trading off with? It's trading off with a bias term, which is these transitions are easy to learn, right? And these transitions are hard to learn, which require a lot of very fine detail, which might not be relevant to our tasks, right? So we can actually look through this bias variance trade-off. We can actually look at Bakary-Emery theory, which looks at diffusion processes, and show that yes, in fact, learning these kind of transitions is easier than this versus learning the last few transitions. So you have a trade-off. Okay, so till where do you actually learn? So it turns out that there is a sweet spot which gives you the best bang for the buck. Okay, as we show through the experiments. Okay. So let me give you one real example before we go to the actual empirical results. So let's say we have something called QM9 dataset, right? So it has a molecule structure, geometric structure of 100,000 molecules. So what are the molecules and where are they in space? And this is the molecule. Okay, where the task is, okay, you show the model these things and ask it to generate new molecules. Okay. So now, okay, so we have pre-trained this model and now we want to fine tune. And then what do we fine tune it on? or RL tune it on, it's something called molecule stability. So there are all these physics-based modeling kits which can tell you how stable a molecule is based on bond angles and based on bond lengths and so on. Okay, and we want to maximize the molecule stability of the output of our generative model. Right, we take this as the reward model. Okay, so now let's look at it. Okay, so we are going through the diffusion process, and after this is the okay, let's say there's an average reward, and if I just give you identical trials of this, whether it is reward 1 or 0 multiple times, it will look at like a binomial distribution to you. And that's what it is if I start out with pure noise, because you have no idea where you end up with. And that is the distribution of 1000 things like this. Now, let's say we denoise till step 3n/4, right? It's slightly denoised. Now we do multiple rollouts, and conditioned on this, we look at the distribution of the final reward. And it looks less like a binomial distribution because it is not actually independent of where we started out with. And now we keep on doing this, and at step n equals capital N/4, where you have done 3/4 of the way of denoising, if you plot the conditional distribution of the rewards, of the average reward, it looks something like this. Is very far away from H0, which is the binomial distribution, right? So this means that you can actually predict whether it will denoise to a stable molecule or not, given that you see the molecule at N/4. So we ask the question, is there any point in training beyond steps N/4? And it turns out there isn't actually, it's counterproductive. You can actually look at the conditional variance of the reward given that we have denoised till here. If you start at 0, you have a large variance in the reward. And if you go on till 3n/4, the variance gets smaller and smaller. At n/4, actually you have a sudden drop in the variance. That means that you can actually, there is a statistical test to actually tell you whether it will reach higher reward or lower reward, which is better than a coin toss. Okay, so here are the actual examples on large scale image modeling and molecule modeling data sets. So, okay, let's say we take text to image generation fine tuning on Stable Diffusion V2. So we have a prompt and we have an image, and we want to say that, okay, does it actually conform to the thing? So if it says there are 3 apples in this image, there should be 3 apples in that image. Okay, so that is the kind of task. So the higher the better the scores. And okay, if you look at this is SDXL base, which has 69%, and SDV2 is the smaller version, which has 66.87% of the overlap. Okay, so DDPO, which removes regularization, actually hurts this value. Okay, you can see that it actually becomes lower compared to pre-training. GRAFT, which is the simplest version, which is rejection sampling based fine tuning, increases it to 70. Okay, and then partial GRAFT with 0.25, where you don't train the last few steps, only train the first few steps, that gives you the best performance with 71.94%, and it's actually seen across the board on various benchmarks and various evaluation data sets, prompts, and so on. Okay, we can actually see this in layout generation and molecule generation as well. This was very stark in molecule generation, where we could not move it at all with any other RL method we tried, but only this partial GRAFT with 0.25n was actually able to make it better than the baseline at all, right? So there is some merit to our method here. Okay, so let me show you some examples. Okay, so the prompt is in the yoga room, all mats are red. This is Stable Diffusion V2, this is DDPO, this is GRAFT, and this is partial GRAFT. Okay, so here it is actually not producing all red mats in that yoga room. Okay, so you might have seen Nano Banana and saying that, okay, this is very low quality, it's because it's a much smaller model, but this is what we got to experiment with last year. Okay, so and then there is this 3 policemen working together to direct traffic at a busy intersection. Okay, so if you just ask the pre-trained model, it would generate something like this, but once you post in it, you get the correct number of policemen here. Okay, you might argue that there's a hidden policeman here, but it's what it is. Okay, so and then there's, if you have a prompt, there's an apple and 2 bananas on the table, and neither of it is bigger than the apple. Okay, if you just send it to SDV2, it forgets to get the second apple, and there's no second banana here. And okay, GRAFT and P-GRAFT can kind of get you, this will get you 2 apples and 2 bananas, this gets you 1 apple and 2 bananas, which is the right answer. So this is what I mean by text to image alignment, right? So we are able to improve these things with post-training. Okay, so RL for diffusion and flow models is a very hot topic of research right now because of all the technical issues I just discussed, and there are a lot of follow-up work and things which are going on right now. Flow GRPO, diffusion NFT, reinforce adjoint matching, and VGRPO. And I would also recommend that you look at this Quen image 2.0 tech report. They give you some details as to how they came up with the new Quen image model and they were able to post-train, which I believe is the first time anyone has revealed these details in public, right? And yeah, I think these are all great resources. How much time do I have left? 15 minutes, okay. Okay, so then I can go into the next phase. We'll be changing gears here, so I can take any questions you might have. Yeah.
So, how do you decide that n by 4 should look up to n by 4 and then how did you come up with that?
So why? Okay, so there are a couple of things. Okay, one is purely theoretically, we looked at when the variance suddenly started dropping. There's an inflection point where we can actually do this multiple rollouts and actually have the statistical test to see that conditional variance drops. The second thing is we actually tried our experiments at various steps and kept the one which gave the best performance. So it's a model selection thing. That's a good question. I don't know. It's a training set. It's usually very hard to control it perfectly well. It's still a very big, much bigger models than this actually refuse to follow your prompt, right? So yeah, it's very hard control problem.
You didn't add a banana. Can you add a banana? Some stuff like. Can we do that?
So there are newer set of models which are like interactive editing models, right? So those things can actually do that. So Stable Diffusion itself cannot do editing very easily especially with interactive thing. But if you look at the professional grade things like Nano Banana or GPT Image, they are able to do the sequential editing.
Will that follow the diffusion process only, or will?
I don't think I can answer that question.
Curiosity.
Yeah. Yeah.
These are like very difficult kind of examples that you're showing, where there needs to be compositional reasoning and all. So when you use a reward model for these methods, is it like it's not going to be a basic clip model, right?
It is something called VQAScore. Visual question answer score. It's actually better than clip actually.
Okay, so like when you then evaluate using VQAScore itself, will it be easier to understand? Meaning,
You're thinking it's hacking the reward.
Could it be hacking?
So basically, we had a different set of prompts for training and evaluation.
Okay.
So we hope that it is that. But yes, you have a very good point in the sense that these are all imperfectly trained models. So you might have actually hacked, but to some extent, it's mitigated by having a different validation set, which is not touched by training.
Okay. One more question. I mean, all this is related to prompt alignment, what you're showing. With respect to quality, I mean, if I want to improve the quality, just like sir asked about the banana not being realistic or something like that. From that point of view, even the last steps are also required for a high quality generation, right?
Correct.
So in terms of, I think, alignment, this is pretty good, but in terms of quality or all those things, is still this kind of early sampling or these things going to help?
Right, okay. So let's look at the flow model equivalent of generation, right? So if I tell you the initial seed, I can actually tell you what image it goes to. So where is the variance coming from? So do you think that if you can actually, okay, let's say in high dimensions, there is a, let's say there's a part which is, let's say you want to reduce the how AI looky it is, right? So there is this part which looks like AI look and this part which doesn't look good. All of them adhere to your prompt, and you have an ODE which can either go here or it can go here, right? You can still control this to some extent so that it goes there. And the problem with training the entire thing is that the amount of data you have is very, very limited. If you try to learn the entire field everywhere, it will lead to overfitting and it won't learn anything. So that's why I believe that it still would be worth looking at training the initial part, especially in these models as well. So it's a bit more, so basically we show that, okay, it converges. So what we are learning is a score function, the grad log PT. So if you go through a OU process, right? So it starts, even the score function starts going to 0 because it decays, right? KL decay implies that it's a, it's a gradient of the KL in some sense. So that also goes down. So basically you have this, you want to learn this grad log PT of x, okay, this plus x squared, integral PT of x is less than or equal to this some c times e to the minus t, right? So what does this mean? It means that as t increases, this is becoming closer and closer to this function x. So you don't actually need very expressive neural networks to capture these. So you just have to search in a very close neighborhood of this simpler function x. So you might need less data. So it's not a very rigorous statement that's saying that, okay, here is the learning theoretic reason this is working. It's just that a smaller class of neural networks are able to capture this function. Exactly, yeah. Because it is closer to Gaussianity, it should be easier to learn the score function, smooth score function. Yeah. It's not actually 100% independent. It's because we use the same schedule, right? So time discretization, it's not uniform. We use the DDPM time discretization, which is very specific. It's like quadratic gaps, quadratically increasing gaps. No, yeah, it's because of the process where it becomes. It's also like a coincidence, I would say. It's it's not necessarily here at all. Yeah. So. Right, okay. So in the next 10 minutes, I'll introduce the last part of this, so which is regarding flow models. How can we improve flow models with some of the intuitions we have? Okay, so this is something called inverse noise correction. So flow models are like the close cousins of diffusion models. They have, they can actually go between those worlds from stochastic differential equations to ODEs via probability flow ODE and so on, and these are all well known. So these things tend to generate images by taking dxt by dt is equal to v theta of t comma xt, where v theta is the neural network which tells me a velocity field through which I can go and take my Gaussian into an image, convert my Gaussian into an image. Okay. So let's say we have x naught looks like this, and x1, and if I go from time 0 to time 1, and it looks like my target distribution x1. Okay. So for flow models, there is no bias variance tradeoff since the output is a function of the initial noise, right? So what is the point of any of the diffusion model stuff I told you, right? Because it's a deterministic ODE. It maps 1 point in x0 to 1 point in p1, right? So let's say this specific white noise instantiation goes to this cat image, this goes to a different one, and this goes to a different one, and so on. And it's deterministic. We can go from the cat to this by reversing the ordinary differential equation. Okay. So we have learned this v theta, and it is discretized in time, and then we go from initial distribution, noise distribution, to image distribution, right, approximately. Okay. There are two sources of error here. Okay. One is the learning error, which is statistical approximation and optimization. Statistical error is because you don't have infinite number of samples. Approximation error is because your neural network is not infinite in size. Optimization is because you have not optimized it to the global fully, completely, even in the empirical thing. Okay. So then there is the discretization error, which is because you're not, you're using a finite difference method to simulate the ODE instead of actually using a continuous integrator, right? So the question is, can we take all these errors and correct them in a sample efficient way? Okay, so the first thing we look at is that flow models are reversible. So if I take this ODE, which takes dxt by dt is v of xt comma t, we can actually reverse it in time by reversing time, replacing time with 1 minus t and replacing the velocity with minus v. Right? It's just basically if you have a video, you just play the video in reverse, and it reverses, it is a way to go from x1 to x0 as long as velocity field is not too singular or whatever, it does no explosion and so on, it is possible. Okay. So basically this is an invertible thing. So if there is a map which is the integration which takes you from x0 to x1, that map is invertible, this T inverse. Okay, and we can show that it is reversible even with discretization as long as step size is not too bad. Okay, okay, so that is actually, you can analyze this using Banach fixed point theorem, that it is actually reversible because its Lipschitz constant is not too large, and there's a large identity here, so that it is kind of reversible as long as the velocity field is Lipschitz. Okay. Okay, so we have flow models are reversible, it's reversible even with discretization, and can we leverage this property for better pre-training, right? So we have noise distribution, we have a learned distribution which is x dot is equal to v theta of xt, and then this is reversible with again minus v theta of x comma 1 minus t. Okay, and then there is a image distribution, and if I take this learned reverse process on the actual images, I get something called the inverse noise distribution. So if I start with Gaussian and run my flow with all these errors, I get a learned distribution. If I go reverse, I get back Gaussian. But now I take this learned reverse thing and apply it on the image distribution, I get something called the inverse noise distribution. Okay, this is supposed to look like Gaussian, okay, but it is not exactly Gaussian. Okay, so and if I use the learned model with discretization on the inverse noise distribution, it will go to the perfect distribution of images. Okay, so here is a free lunch. That is, if I can somehow sample from this inverse noise distribution from the noise distribution, it is slightly non-Gaussian, almost Gaussian but slightly non-Gaussian distribution from the Gaussian distribution, I can use my learned model to get to the perfect image distribution. Okay, so that is the inverse noise correction, right? And we hope that this is easier to learn, because we hope that it is easier to go to a slightly non-Gaussian distribution from a Gaussian distribution than it is to go from a Gaussian distribution to something which is very far away, like the space of images, right? So that is what inverse noise correction is. And then if you let me show you some examples here. And so if I have noise and flow model and image, it somewhat looks like this. But if you do noise and some correction and then flow model, and it actually removes a lot of the artifacts which are present here, especially images like this and so on. Okay. Okay. So we trained it on image models. So actually it allows a lot of things. For example, you can actually get very good quality with lower number of steps and lower number of flops, even if you add this new set of inverse noise correction model, because it is correcting the errors introduced by the larger model, right? You can actually have more efficient inference. Okay, if we go to Celebi HQ, right, a data set, if you just had the pre-trained model with 1000 steps, it's able to reach 11.93 FID. With 200 steps, it's 11.39. And the number of flops is 1.374 teraflops of computation, right? But if I do a small corrector, it's like 1/4 the size of this, and run it for 200 steps and 200 steps, and it's here, and it is actually a much better FID at actually a lower amount of teraflops of compute, right? It's actually more compute efficient and gives you better images just by doing this better statistical procedure, which was inspired by our prior investigation. Okay, so let me end the talk here and make room for any last questions. Yeah, please. Right. Right. So because you would have pre-trained the Sudoku, right? In the sense that, okay, you have 100,000 Sudoku models, as in, okay, so here's the right question to ask, okay? I'll give you 100,000 correct Sudokus, and then I'll mask and I'll try to make it learn how to solve it, basically. But I won't tell it that it's actually solving a Sudoku, okay? And then you wanted to magically figure out that with this 100,000 thing, it has to, all the rows have to be 1 to 9, columns have to be 1 to 9, and small boxes have to be 1 to 9, right? So that is what pre-training does. In post-training, what do? You ask it to do multiple rollouts, right? And then you actually go and use a checker to say that, okay, this is, maybe it achieves 80% accuracy. Even though you have not told it that it is solving Sudoku, it has kind of figured out statistically that this is what it has to do. Now you show it to a computer program and actually rate it. Now you figure out that it has 80% accuracy. Now you do multiple rollouts from the same thing, and you have 80% of them being correct, right? And you pick the correct ones and reinsert it back. Okay, now you go to the partially thing. Okay, you ask the question, when did it go wrong? It could have gone wrong in the last n by 4, it could have gone wrong in the first n by 4, right? If it can actually correct the things where it went wrong in the initial few steps, the Sudoku, right? It might have added 2 9s in the same place, and it's already visible in the initial few steps, and it will go and correct that with the reward model, right? Yeah. So, yeah. Okay.